So the next problem I'm going to review from the chapter review is number 33. In number 33, it states to use the data in table 8.1, and we're trying to compute the gravitational force that the sun exerts on Jupiter. So what we need to first evaluate is what are they asking, and they're basically asking what's the force of attraction between two objects. Well, we now know from the universal gravitational formula that we can get that force by using G m1 m2 all over r squared, the distance they're apart. And then it's simply just subbing in the data. Well, G is the universal gravitational constant that we will be using throughout this chapter. That is 6.67 times 10 to the negative 11 newtons meters squared kilograms squared as the units. And I always recommend keeping the units in there so that you know when you cancel out, you're moving in the right direction. So the mass of object 1, let's talk about the mass of the sun just because that's the order that they're given in the problem. And the mass of the sun is given in the table is 1.99 times 10 to the 30th kilograms. Really, really big. One of the biggest objects that we know that we can see that is having a physical effect on us in the solar system. But obviously black holes, and there are much, much bigger stars than our sun. The next object in the solar system that we're comparing to is the mass of Jupiter. The mass of Jupiter is the largest planet in our solar system, but it still doesn't meet up to what the sun is. So it's 1.90 times 10 to the 27th kilograms. Now, one of the last pieces of data we need to solve here is the radius in between them, the distance between them. As I mentioned before, we just need to use the radius between them. Technically, if we wanted to add in the radius of Jupiter, which is significant, and the radius of the sun, it would have a minute part in changing the value here. But since we're just in CP physics, we're not really going to worry about that at the moment. So we're just going to put in the radius, and we got all this information from the table, is 7.78 times 10 to the 11th meters. Key is meters, because that is what our universal gravitation is in. So now, this is simply just subbing it in. So we have G, 6.67 times 10 to the negative 11 Newton meter squared kilograms squared. The mass of our first object, which we will do the sun, is 1.99 times 10 to the 30th kilograms. Then we have the mass of Jupiter, which is 1.90 times 10 to the 27th kilograms, all over 7.78 times 10 to the 11th meters, make that squared. And when you do that, the kilograms will cancel out this exponent. This kilogram will cancel out the kilograms there. This meters over here, since it is squared right here, this will cancel out over here. And now we know that our answer is going to be in newtons. We're moving in the right direction. But this is the most difficult part of the problem in putting this into the calculator. You have exponents, you have times 10 to the, and then you have everything division put in there. So please be careful when you're putting it into the calculator, one unit at a time. And just remember, multiply everything at the top, multiply, 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 and then divide by everything on the bottom, but be sure to keep it in parentheses. Be careful, take your time doing this, but you will get it. Just be careful in the calculator, and everybody's calculator is different, and I can't have instructions per calculator, but just try it, take your time, and I'm sure you'll get the answer. And the answer here comes out to 4.17 times 10 to the 23rd newtons. And 2 decimal places is more than fine. Remember, the textbook answers usually round to significant figures, which is not necessary in CP physics at the point. But just do your best to try this out and practice, practice, practice.